Suppose we have a hot end and a cold end.
Yes.
The cold end is fixed.
No, I mean, you keep gesturing with different hand. Hot and cold, not, and then you said cold and hot. But okay, hot and cold, yes, they're fixed, yes.
Yeah. So suppose at the hot end, we start increasing the temperature.
Yes, yes,
That
that's-
is, we are actually changing the boundary conditions.
No, we are not. You might think we are, but not quite, because we've all done this non-dimensionalization here. I would say we're changing the Rayleigh number. We have defined T to have the values 0 and 1 here, and so what we're changing, we have absorbed that in there. The values are 1 and 0, and of the perturbation, they are 0 and 0, and when you change that temperature, we've arranged things in such a way that you're changing the Rayleigh number.
Then maybe let us think in terms of the perturbation.
Yes, I'm thinking in terms of the perturbation.
Yeah, so suppose we start increasing the perturbation and we notice
The
that,
amplitude of the perturbation.
yeah, the amplitude of the perturbation, and we notice at one point the instability starts. Does that mean we have hit the space equal to one line?
I don't think you can think in those terms either. This is linear stability analysis. Your perturbation is infinitesimal. It does not have a size. It is small. When you have a linear problem, like epsilon dot equals f prime of x bar epsilon, epsilon has no size. You can multiply both sides of this equation by any constant. Once you've reduced your, of course you're assuming that epsilon is small because you have taken away this term here. But the idea that you're going to increase the initial amplitude is not described in this formalism. I'm not sure if I properly answered your question, but that's not what you look at there.
So to forgive the native question, the circles you've drawn for cables 1, 2, and 3, those
Yes.
are convection vortices.
Uh-huh.
So that if we've increased the Rayleigh number until it hits a point where that begins effectively. So below that there's no convection.
That's right.
Above that we get this convection. So
Yes.
Cool. That was
That's
my
right,
choice.
that's right. But it's not that as we increase the Rayleigh number, we get this, and then we get this, and then we get this. We are above all of these, by the time we're here, we're above all of these curves. All of those are unstable, but most likely if we're increasing gradually, what has happened here is convection has set in with the single roll, and we are no longer interested in what is the stability of a layer without any rolls, because that's not our situation anymore. This is merely a tool in order to determine which instability arises first. We take all of this information and we reduce it to this one point.
So there wouldn't be any mode hopping or anything between the two. It wouldn't matter because those
There might be, but that would require further studies and secondary bifurcations and other things. All this is telling us is that this is the first thing to happen. There will be a bifurcation, which will be a pitchfork bifurcation for the reasons that we will describe in the next class called symmetry. And then, if we linger on this, it will grow and reach it will be a pitchfork bifurcation, where you will then have something like this that grows to finite. Okay. In terms of what we did last time, where you recall this is the amplitude of something, and this is the Rayleigh number. Okay. Remember, we drew arrows like this. What we have been describing, all of this stuff that we've been describing, is these arrows. These arrows have changed directions at this bifurcation point. And we've been discussing the fact that this changes from being solid to being dashed, meaning it's unstable. Where it goes afterwards, that's a different matter. And that there's this here is not being described by linear stability analysis. All that's being described is the fact that these arrows have changed from contracting to expanding.
So for any those shapes that you've drawn
Yes.
are contours of psi, and
Yes.
they would look completely the same regardless of what your eigenvalue is. They'd just be whether they're grown or not. They would have the same shape.
That's right. They would have the same, the
Your choice
spatial
of-
features,
your choice of K.
the spatial features are described here.
Yeah.
And now we've been discussing, for a given spatial description, what is that lambda like? When does it stop change, this lambda is a function. Okay, once you plug this functional form into this, including the lambda, you will find that lambda is a function of Rayleigh number and Prandtl number, as well as q and k. We saw it's not a function of Prandtl number. It's going to be a function of q, and the lambda will be a function of q, k, and Rayleigh number. Lambda will be, you agree? If you plug it in here, you'll find that lambda is a function of q, k, Rayleigh number, and Prandtl number. We found it wasn't a function of Prandtl number. It's still a function of Rayleigh number, but now we do another step, which is to say we set lambda to be, you can see that this is an eigenvalue problem. Those lambdas are functions of Prandtl number, gamma, which is just a combination of q and k, and Rayleigh number. But now, if we set lambda equal to 0, we get an implicit function. We get a function Ra that depends only on q and k, and this Ra equals gamma 6 over q squared. This is what satisfies lambda equals 0 here. But we can stay here until everybody is satisfied. Really, it's not a problem.
So I had a question. If you're at a Rayleigh number where you have more than one k for which lambda has a positive real part, is k equal 1, like, is that going to give you the largest real part?
It will. It will. I mean, it didn't quite have to from this, but as it happens, this Rayleigh number here, the lambdas grow monotonically from this. These are the curves where the lambdas are 0, and they grow from this. And by the time you hit here, where a second lambda is 0, this one has become so large that, of course, it has grown way beyond anything that you would be interested in here. And as I said, if you linger on the Rayleigh number, okay. Another thing about linear stability analysis, this was all well and good what we said to take out this epsilon squared, right? Because if epsilon is small, well then epsilon squared is even smaller. That's true, except that if we find that epsilon of t is e to the lambda t epsilon of 0, and lambda is positive, this is not going to stay small for that long. Right? So linear stability analysis tells you about the beginning. That's what I meant when I erased this curves here. It tells you I'm leaving, but then it doesn't tell you after. Then you can't think about linear stability analysis more because you're gone and your epsilon is big, your epsilon squared is not negligible, and everything you've done is wrong. It tells you it remains accurate when lambda is negative. When lambda is 0, if this guy is smaller, then if epsilon is small, then it remains small. It gets even smaller. It gets even smaller. So the stability, that part is right. We're right to say, okay, this is coming down to this, and it's staying here, and we don't have to learn anything more. It's all going to go down and down and down and down, and linear stability analysis is going to remain not just be true, but even truer as you go along. But on this side, it's not true as you go along. It's true in the beginning. You leave. Your next step is not clear. I mean, it is clear. It's going to be clear. But this is not the province of linear stability analysis. The province of linear stability analysis is I leave. But you know that yourself. If you say I'm staying, then you don't have anything more to say. You're here. You're staying. If you say I'm leaving, well, then somebody might say, and where are you going, please? Right? There's more to the story.
All right, so go back to the slide. So, yeah, this. So you're solving the characteristic equation of this little system, but you said lambda is equal to 0, so you're just taking the determinant of that matrix.
Let me write those steps just as you say. That thing above has lambda as a function of Rayleigh number, Prandtl number, q, and k. That's what this would give you. If you would write the formula for the eigenvalues of this 2x2 matrix, right? And that's what you would get. Now you do two other things. One of them is you set lambda equals 0, and that is going. Once you set lambda equals 0, I shouldn't say lambda. I should say some function of, what should I call the function? Let's call it g. Okay, once I've set lambda equal to 0, I now have, I can set one of these to a function of the three others. Right? I'm going to say Rayleigh number is equal to some function, I'll write A as h of p, r, q, and k. I learned from this equation here that it actually doesn't depend on pr, that the pr dropped out. And this function here is the one that we call REC of q and k.
That first black equation is just the determinant of that.
That's right, that's right. That's just the determinant of that 2 by 2 block. That is the solution to, that is writing this with lambda equals 0. Okay, and all this is the equivalent for us, a special case of finding the eigenvalues of a fixed, of the Jacobian matrix of a fixed point. And then looking for when one of them becomes positive. Okay? Everything good? Okay. So, this is just a formula for those little black dots, and that black dot is 27/4 pi to the 4th classic value, 657. If we had done the whole thing with rigid boundaries, instead of those sine k pi z's, we would have used Chandrasekhar functions. Everything would have been qualitatively the same, but quantitatively different. And what we would find, yeah, let me go back here and say what we found. You see that this lowest value is found here, pi, for q equals pi over square root of 2. And q equals, let's talk about what that means. Q equals pi over square root of 2. What's the wavelength of that? That is, okay, so the wavelength, I don't want to call it lambda because we have lambda for the growth rate. Wavelength, what could we use?
Gamma.
Oh, no,
No,
we're using, no. Okay, I'm just going to write wavelength
Psi or something.
equals, no, we're using psi also. No. Wavelength equals 2 pi over q, which is equal to 2 pi over square root of 2. Do I have that right? Yeah. And so that is 2 times square root of 2. Square root of 2 is 1.4, isn't it? Something like that?
142.
Yeah, 1.4, something like that. Okay, a wavelength, that's going to be, oh, I erased them. I was writing these things. This is the k equal 2 thing. Oh, let me not be confusing by writing k equal 2. Let me write 1 here. So this is a convection roll like this, and this is the wavelength here. So a single roll is going to be half a wavelength, so a roll width is going to be square root of 2, which is about 1.4. So this, if this is 1, which it is by the non-dimensionalization, this is 1.4 from here to here. Okay. If you do the whole thing with rigid boundaries, you get the more satisfying result that the q turns out to be pi and not pi over square root of 2, and hence the wavelength turns out to be 2 pi over pi. The wavelength is 2 and a single roll is 1. So what it wants to do, this is not satisfying, what it wants to do is to make little round things. What the free slip case wants to do is make elliptical things, and what the rigid boundary one wants to do is make circular things. It's not exactly pi, so it's not exactly 1, but pretty close. So everybody sees how you would do the same thing over, except you couldn't do things here you can see we took the derivatives. Taking the derivatives just got us a k pi squared. You know, how easy is that? If it were a Chandrasekhar function, Chandrasekhar's book is this thick, and it was written in the 1950s, and it consists a lot of tabulating functions, because that's what you did in those days. You did not have, you had books, even I still have books, with tabulations of functions, and you learn techniques for interpolating between them, and you use slide rules and all that. But of course, and if you were around in those days, you would be learning those techniques yourself, because it's how you would actually solve problems. But nowadays, there's only need for two kinds of problems. One of them is conceptual and simple problems that you can do with very little calculation, as we have just done, so that you get an understanding. And then the other one is the exact one that you do with a computer to 16-digit precision. There is no need for learning approximations to get 3 or 4 or 5 digits, and how you approximate curvy things and slide rules and all that stuff, because it's just as easy to get pretty much the exact answer. But there's still plenty of use for very simplified problems, which give you a qualitative understanding. And it's fortunate for me, because I wasn't very good at that asymptotic stuff, but it turned out I didn't need to learn. Okay? So maybe now is a good time to take a break, because this is now the end of the convection part. And now we remember this class is about convection and Lorentz system. And so we'll discuss Lorentz system in 15 minutes.